Non-resident training course, September 1998, Navy Electricity and Electronic Training Series, Module 7, Introduction to Solid-State Devices and Power Supply. Chapter 4, Solid-State Power Supply. Learning objectives. Upon completion of this chapter, you'll be able to identify the variation of power supply, state the purpose of each section of power supply, description of the describe the operation power supply, but with the whole unit standpoint from the sum unit standpoint. Describe the purpose of the various type of the rectifier circuit within the power supply. Describe the powers various type of filter circuits used within the power supply. Describe the operation of various voltage current regulators in the power supply. Describe the operation of various type of voltage multipliers. Trace the flow of the AC and DC power supply with the AC input with the DC output on the schematic diagram. Identify the fault component through the visual checks. Identify the problems with a specific area of the power supply by using low logical isolation method of troubleshooting. Apply safety precautions when working with electronic power supply. In today's Navy electronic equipment, both the shore with the board chip that required for the power supply with the discovery of silicone diodes and other solid-state components made possible the reduction side with the increase of the reliability of the electronic equipment. This is especially important on the board chip where the space is accessible with the spare parts of the major concern. In chapters, we will read individual section power supply with their components and purposes for each of the power supply. The basic power supply. View A, Figure 4.1, show the block diagram. Basic power supply. Power supplies are made of 4 basic sections: transformer, rectifier, filter, and regulator. Transformer, rectifier, filter, regulator. Illustrated in view B with the figure 4.1. The first section of the transformer that sets up and steps up or steps down the input line voltage isolated with the power supply with the power line. The rectifier section covered the alternating input signal with the pulsating DC. However, as proceeded in this chapter, you will learn that pulsating DC is not desirable. For the reason the filter section is the converting pulsating DC to a purer, more desirable form of DC voltage. Alright, you have 115 volts AC. It steps up 1 to 3, then 340 volts, 5 volts peak to peak rectifier bridge. Then change it into a pulsating DC with a filter, and then 110 volt average with a ripple. Which is about 66 or 77.1% regulator, 110 volt DC. Final section with the regulator just for the name of the imply that maintains the output of the power supply with the constant level despite with the retain with the load current with the input line voltage. Now that you know that what each of the sections over, let's trace the AC power signal through the power supply, and this is the point where you need to know how the signal is alterated with each section of the power supply. Later on in the chapter, you will see how the change will take place. In view B, with the figure 4.1, input signals 115 volts AC applied with the primary transformer. Transformer is a step-up transformer in a turn ratio of the 1 to 3. The calculated output of the transformer multiplying with the input voltage of the ratio turn for the primary ratio, turn secondary, therefore 115 volts for the AC goes to 345 volts peak to peak, and an output because of either the diode rectifier section conducts 180 degrees with the 360 degrees input with the rectifier is 1/2 of that, approximately 173 volts pulsating DC. The filter section network resistor, capacitor, inductors control and rise the fault time of the varying of the signal. Consequently, the signal remains at more constant DC level. We will see the filter process more clearly. Discussion of actual filter circuits. Output of the filter signal is 110 volts DC with the ripple riding on the DC. The reason for the lower voltage, average voltage, will be explained later in this chapter. The regulator maintains its output in a constant 110 volt DC level, which is used for the electronic equipment more commonly called the load. Power transformer. In some cases, the power supply made with the, not used for the transformer, for the power supply will be connected directly with the source line with the voltage. The typical connection for the use primarily because of the economically, however, the unless the power supply is completely insulated and presents a dangerous shock hazard to anyone who comes in contact with it. The transformer is not being used. The return side of the action line. AC line is connected with the metal shaft to remove the potential shock hazard to have the optional stepping up or step down input voltage rectifier transformer may use. View figure 4.2 shows the schematic diagram of the step-up transformer. View B shows the step-down transformer. View C shows the step-up center tap the transformer. The step-up the step-down transformers views are discussed in the Neets earlier Neets model, so only the center tap transformers will be mentioned in this chapter. The primary proof of the center tap transformer is to provide 2 equal volts of the conventional full-wave rectifier. 115 volts 1 to 3 step up, 340 volts AC, 115 volts 2 to 1 step down, 57 volts AC, 115 volts center tapped, 173. You have the 1 to 3, like, alright, 173, 340 volts AC, and 2 step down, step up. The rectifier. Previous discussion should know the rectification current conversion of the alternating current with a pulsating direction direct current. Now let's see how the process of the rectification occurs both of the halfway and the full wave rectifier. Your half-wave rectifier. Since the silicon diode was present in only one direction, ideally suited for the converting and alternating a current with a direct current into direct current with the AC voltage applied with the diode conducts only part of the alteration with the voltage. That is when the anode of the diode is part with respect with the cathode. Simplest type of the rectifier is half-wave and rectifier shown with the view A of figure 4.3. Half-wave rectifiers use only one diode during the positive alteration input for the voltage. Same way that applied with the diode make for the anode positive with respect over the cathode. The diode conduct for the current of the amperes flow for the direction of the supply lead. Secondary for the transformer through the milliampere through the diode. The positive supply leads indicated by shaded area output waveform in the view B with the current existed during the entire period of time. The anode power with respect with the cathode. In other words, first 180 degrees for the input, sine wave, half-wave rectifier, 120 degrees. Resistant load, milliamperes, rectifier. Alright, 0, 90, 90, 180 conducting cutoff. Simple half-wave rectifier output waveform. During the negative alteration input voltage of the dotted polarity sign of the anode is the derivative of the negative of the diode cannot conduct. When conditioned with such that these exist for the diode for the cutoff for the remains of the cutoff of the 180 degrees during the time of the no current flow for the limited circuit and the circuit current through therefore has an appearance of shear with the positive pulses illustrated with the shaded area of the waveform, and in view with the B with the notice that all the current in the form of the pulses current flows in the same direction current flow for the pulse with the same direction pulsating DC. The diode has thus rectified AC input voltage. Alright, root mean squared peak and average value. The view A figure 4.4 comparison of the root mean squared peak and average value of the type of the waveform so associated with the halfway rectifier. AC voltage is normally specified in terms of the root mean squared value. Thus 115 volts AC power is mentioned in the chapter specifying the root mean square value of 115 volts as in terms of peak value. So you have volts and root mean squared is equal to volts peak at 1707 times 707. Peak value is always higher than the root mean square value. Volts peak is equal to volts root mean squared times 1.414. Therefore, root mean square value of 115 volts AC, but the peak value would be the volt peak value of 115 volts root mean squared times 1.414, 162.6. Figure 4.4 A the comparison of the volt peak of the volt average of the halfway rectifier volt peak waveform. The average value of the sim wave is 0 volts with the figure view B with the figure 4.4 show the average voltage with the chart of the negative portion. Sin wave of the clipped off since the wave has swings on top of the head but never negative path of the 0 volt reference line. Average voltage is part of the average voltage as determined by this equation. Average voltage is equal to average peak times 3.18, or which would be 162.6 volts times 3.8, 51.7 volts. 4/4 of the comparison. Peak volt peak is 2 volts. Average halfway rectifier volt peak waveform 162 volts, 51.7 volts average. Alright, your ripple frequency. Halfway rectifier gets the name of the fact that it conducts during the only half input cycle of the output with the shear of the pulse of the frequency of the same input frequency. Thus, when the operated with a 60 Hz line, the frequency of the pulse is 60 Hz. This is called the ripple frequency. Conventional full rectifier. A full wave rectifier is a device that has 2 or more diodes arranged in load current flow for the same direction during each half cycle of the AC supply. The diagram simple full wave rectifier shown figure 4.5. The transformer supply for the source of the voltage of the 2 diode rectifier with the D1 and D2. Power transformers center tapped and high voltage secondary winding is divided into 2 equal parts. Winding 1, winding 2. Winding 1 provides the source of voltage for the diode rectifier 1, and winding 2 provided the source of voltage for the diode 2. Rectifier 2, the connection of the two diodes arranged for the diodes conduct for the alternating half cycle. The direction of one of the alternating secondary voltage polarities are shown view A of the source of the diode 2. Voltage induced in the lower half of the secondary winding of the transformer winding W2 at the specific instant time as shown in the figure with the anode voltage of the diode 2 is negative. Diode 2 cannot conduct, therefore the period of the time of the anode of the diode negative is negative. Anode diode 1 is positive. Since the anode diode 1 is positive, the conduct for the current causing current to flow through the load resistor in the direction shown by the arrow. Alright, positive alteration. 115 volt step down center taps which gives you positive, and it's running from winding 1 down to diode rectifier number 2 across the load and diode 1 again. Alright, view B show the next half cycle of the secondary voltage in the new polarity with the winding 1, winding 2. The reverse during this alteration, the anode diode D1 negative drive negative diode D1 cannot conduct forward. The near of the time the anode diode D1 is negative, the anode diode T2 is positive, permitting diode D2 to conduct the nodes for the anode current with the diode 2. Passes through the load resistance same direction with the current with the diode 1. The circuit arrangement pole with the load current during each of the alteration input cycle such both alteration input voltage cycle are used as called the full wave rectifier. Or show the negative alteration. Now you have the basic understanding how a full wave rectifier works. Let's cover the detailed practical full wave rectifier and its waveform. Practical full wave rectifier. Practical full wave rectifier circuit shown in the UA with the figure 4-6 with the two diodes D1 and D2 center tap transformer T1 with the center tap of the ground voltage for the opposite for the end with the secondary winding 180 degrees out of the base with each other when the voltage point with the positive with respect with the ground, the voltage point B, the negative with respect with the ground. Let's examine the operation equal of a circuit during one complete cycle. Show the rectifier circuit with its center tap and also the associated wave variance load voltage and secondary voltage. During the first half cycle, the indicated solid area for the anode diode 1, positive with respect with the ground with the anode diode 2. The negative is shown with the current flow with the ground and center tap through the load resistor in the diode 1 to the point A. The transformer current flows from point A through the upper winding with the background and center tap of the diode 1 conduct with the axis of the likely closed switch to the positive half cycle with the held across the load resistor. During the second half cycle, they indicate with the dotted line is polarity applied voltage reverse. Now that the anode of the diode 2 is positive with respect to the ground of the anode diode 1, negative now that only diode 2 can conduct. Current now flows and shown the ground center tap up through the load resistor RL through the diode 2 with the deployment with B with the transformer 1. Transformer current flow with the built point B through the lower windings back to the ground center tap. Note that the current flow with the load resistor in the same direction both halves the input voltage. Input cycle. View B represents the output waveform, the whole full wave rectifier, the waveform of the consists of the two poles for the current over the voltage for each cycle of the input, the ripple frequency of the output with the full wave rectifier is therefore twice the line frequency. Frequency is output with the full rectifiers offers the distinct advantage because of the high ripple frequency. Output closely approximate to pure DC. The higher frequency almost filtering each for the easier than the output half wave rectifier. In terms of peak value of the average value of the current with the voltage of the output with the full wave rectifier twice the grade of the output for a half wave rectifier, the relationship between the peak value and the average voltage value of the illustrated 4/7 into the output waveform is essentially same wave with both alterations, same polarity. Average current voltage is 63% of the peak current voltage. Peak value area A, area B, area A equals area B, amperes or volts. An equation: voltage max is the peak value of the load voltage plus voltage max 0.637 times the voltage max is the average load of the average load of the voltage. Amperes max with the peak value of the load current times the average of amps is 0.63 times the amps max, the average load current. Sample the total voltage graph of the high voltage secondary of the transformer U that is supplied with a full wave rectifier 300 volts of the average load voltage, ignoring the drop across of the diode. Since the solution total secondary of the voltage secondary voltage is 300 volts, U the diode supplied 1/2 of the volt value with 150 volts both. Because of the secondary voltage of the root mean square of the peak load value is the voltage max is on 1.414 times 150 or 212 volts. Average load voltage is 0.63 times the volt max is 135 volts. No, if you have problems with this equation, review the portion of the Neets Module 2 pertaining to the subject. As you recall, the capacitive with electricity, average circuit with the advantage, with the disadvantage, full rectifier, no exemption. Instead of the full wave rectifier, you have the founding with the doubling of the output frequency, the average voltage with the double the resulting circuit with the much easier for the filter because of the ripple frequency. Only disadvantage with the peak voltage in full wave rectifier is only the half bit of the peak with a half wave rectifier. This is all because of the secondary power transformer, the full wave rectifier center tap. Therefore, only 1/2 of the source of the voltage goes to each diode. Fortunately, the rectifier which produces the same peak as the voltage as half wave rectifier with a simpler frequency with the full rectifier circuit known as the bridge circuit rectifier will be shown in the next discussion. Bridge rectifier. Alright, your 4 diodes connect with the figure 4-8 with the circuit with the bridge rectifier input with the circuit with the applied with the diagonal opposite with the corner of the network output with the taken with the remaining 2 corners. Show the bridge rectifier diodes in the 1, 2, 3, 4 resistant load and transformer tamping wiring and sim waves. 1, 2, 3, 4, 5. On completing the cycle with the operation, we'll discover to help you understand what the circuit works. We have to discover the transformer, perform with the module, the Neets series. We'll go with either with the character of the time. At the time, let us assume with the transformer is working properly. There's a positive potential at point A, negative potential at point B. The positive potential at point A is forward bias with the direction of the diode 3, with the reverse bias at diode 4. The negative potential at the point B with a forward bias at diode 1 and reverse bias at bias at diode 2. At this time, the diode 3 and diode 1 forward bias will current flow through the path of the diode 4 and diode 2. Our reverse bias will block the current flow. The path of the current flowing for the point D with the diode 1 up through the resistant load with the diode 3 with the secondary with the transformer back in the point B. This path indicates the solid area of the waveforms 1 and 2 can be observed across the diode 1 and diode 3. 1/2 circle and 1/2 cycle later, the polarity across the secondary transformer reverses the forward biasing diode 1 and diode 2, reversing the diode 1 and diode 3. Current flow will now be with the point A through D4 through the resistant load resistor. With the diode 2 with a secondary transformer backing winding transformer T1 back to the point A with an indicator with the broken arrows. The waveforms 3 and 4 can be observed with the diode 2 and diode 4. You should have noted that the current flowing with the load resistor always in the same direction, flowing through the road resistor. Current develops the voltage crossing is shown with the waveform 5 of the current flow with the load resistor during both half cycles applied voltage in the bridge rectifier, full rectifier. On the advantage of the bridge rectifier over the conventional full wave rectifier that is given in the transformer, the bridge rectifier produces the voltage output with nearly twice as the conventional full with a wave circuit. This has been shown the sign of the value of the components and shown in views A and B with figure 4-9. Assume that some of the same transformers in both circuit with the lake volts are developed between X and Y and is 1000 volts for the both circuit with the conventional full wave circuit shown in view A with the peak voltage with center tap of the X and or Y 500 volts. Since only one diode can conduct an instant with the maximum voltage can be rectified at an instant 500 volts. Therefore, the maximum voltage appear across the load resistor now is that never exceeds 500 volts. As a result of the small voltage dropped across the diode, the bridge rectifier shown in view B with the maximum voltage rectifier full secondary voltage with 1000 volts. Therefore, peak output voltage across the load resistor normally 1000 volts, which with the both circuit of the same transformer with the bridge rectifier curve produces the higher output voltage conventional full wave rectifier circuit. A shows the conventional full wave rectifier. Comparison with the conventional bridge rectifier with the conventional full wave rectifier, bridge rectifier, diode 1, 2, 3, 4. Filters. While output for the rectifier pulsating, the DC most electronic circuit requires substantial pure DC proper operation. The type of the output provided with a single multi-section filter circuit to place between the output rectifier and the load. There are 4 basic filter circuits, simple capacitor filter, LC choke up input choke input filter, LC capacitor input filter, RC and capacitor input filter. Functions of each of these filters will be covered in detail within this chapter. Filtering accomplished with the use of the capacitor indicator the resistor vary for the combination indicator the series of the input impedance for the oppose of the flowing with operation pulsating DC current with the capacitors are shown with the elements with the high passing element alternating component with a single round with low with the ground with the resistor U with the play for the indicator and flow current applications. Let's briefly review the property of the capacitor. With the capacitor output with the any chain with the voltage of the input opposition chain with the current with the capacitive reactance with the measure of the ohms. The capacitive reactance determine the frequency of the applied voltage capacity of the capacitor. So the capacitive reactance is equal to 1 times the 2 times the farad times the capacity is 1.59 times the formula you can see with the frequency capacity is increased with the capacity reactance decreases since filter capacitors are playable well with the low the capacity the reactance will provide with the filter with a high capacity reactance for accomplish better shunting effect with around load and provide with the shown figure 410. To obtain steady DC output with this capacitor must charge almost instantaneously with the value applied with the voltage. One shot of the capacitor may retain charge along the top of the capacitor must have a short time constant. View A, this change this can be like keeping the internal resistance power supply as small as possible. The first charge time, the resistance of the load is the largest possible as a slow discharge time illustrated in view B. View 410A shows the capacitor fast charge power supply, capacitor charge time load, and view B shows the slow discharge capacitor going to the low discharge path. From earlier study of the basic lectures, you may remember the one-time constant is defined at the time of the capacitor with 63.2 the percent of the applied with the voltage discharge of 36.8% of the total charge. For the action is expressed with the following equation. Time is equal to the resistance, the representative resistance and charge of the discharge path of and C representative of the capacity of the capacitor. So R times C. You should recall the capacitor is considered the full wave rectifier 5 RC time constants. Refer to the figure 411. You can see with the steady DC output is obtained with the capacitor changes as rapidly and discharge as slowly possible. And then we're going to pause it right here. Alright, once again, we're back to 411, resistor capacitor time constant, percent of the charge of the discharge, 1 RC, 2 RC, 3 RC, 4 R, 5 RC time constant, 36.8, 63.2, 86, shows your charge and discharge. Filter restrict for the capacitor with the common element of both of the charge of the discharge path. Therefore, they obtain the longest period of the possible discharge. You want the capacitor as large as possible. Another way to look at it with the capacitor actually short circuit around the load. As far as the AC component is concerned, with the capacitive reactance equal to 1 over times 2 times 5 times the capacitor. Larger value with the capacitor, smaller with the opposition with the capacitor reactance or reactance to the AC. Now let's look at the inductor for the application filter circle. Remember the inductor will over the any chain with the current indicate over the forgotten chain with the current through the introduction produced with the changing electromagnetic field, the chain with the internal with the cut of the winding for the wires, the indicator inductor thereby producing counter electrical EM found with a counter electric EM electromagnetic force for that over the chain with the circuit current with the opposition of the chain with the current is frequently called with the inductive reactance mentioned and on, but the inductive reactance of an inductor is determined by the applied frequency indication of the indicator. Mathematically, the inductive reactance is equal to 2 times pi times F times the load times the inductance. Frequency inductance increase the inductive reactance if the increase of the inductors are placed in series of loads shown in figure 412. The inductance resistance is larger AC voltage is developed across the load. Figure 412 show that this power supply, large AC voltage capacitor 1 load and small load AC voltage drop. Now refer to figure 413 when the current starts with the flow through the coil expanding magnetic field with the builds up around the indicator the magnetic field with the coil develops the counter EMF with the opposed to the chain with the current with the reactive current with the decrease with the figure 414 magnetic field collapses against for the turn with the winding with the wire thus indicating the current with the coil. The additional currents merge with the rectifier current to attempt to keep the original level. Power supply expanding magnetic field with counter EMF with capacitor 1 load. Alright, load to the induced current with the capacitive magnetic cores. Now you have the read how the component of the filter circuit with the current flow for the rectifier, different type of the filter circuit that have to be discussed. The capacitor filter, the simple capacitor filter, the most basic type of the power supply filtration application for the simple capacitor filter, limited with sometimes used with extremely high voltage, low current power with the supply with a cathode ray similar electron tubes require a little load current with them for the supply with the capacitor filled with the use of the power supply. Ripple frequency is not critical. The frequency can be relatively high with the capacitor shown with figure 415. Simple filter connect with the cross with the output with the rectifier is parallel with the load. 415 full wave rectifier with a capacitor. Capacitor is ground with a resistant load with the diode 1, diode 2, transformer 1, T winding. That is your full wave rectifier capacitor filter drawing. The filter you with the resisting capacitor charge time of the filter capacitor must show up with the RC discharge time much along with the eliminating ripple. In other words, the capacitor must charge up after preferably discharge at all, with no discharge at all before filtering. Also, result of the infrequency of the high, therefore full wave rectifier output with the cause of either of the filter with the halfway rectifier because of the higher frequencies. If you have better understanding of the effect of the voltage of the comparison with the rectifier circuit through the filter, one of the filters illustrated views A and B of figure 416. The output waveforms of figure 416 represent the unfiltered filtered operation of the half-wave rectifier circuit with the current pulse through the load resistant for the time diode contact. Note the dash line indicates the average voltage output voltage for the half-wave rectifier voltage average less than half of the approximately 0.31A. Peak output voltage value is still much less than applied voltage of the common capacitor connected with the output voltage rectifier current with the waveform view A as large pulsating component ripple compared with the average of the DC component. The capacitor is connected across the output output of UB with the average value of the output voltage average on voltage average increased due to the filter action of the capacitor 1. Figure 1416A show the halfway rectifier with and without filtering. Transformer T1 winding grounded resistor load diode 1. Transformer B filter shows the transformer T1 diode 1 C1 grounded resistor load. Value of the capacitor of the fairly large microfarads with the representative of the relatively low resistance of the pulsating current stored with a substantial charge. The rate of the charge of the capacitor is limited only resistance of the conducting diode, which is relatively high. Therefore, the RC charge time of the circuit is relatively short, and result of the pulsating voltage first applied to the circuit of the capacitor charge rapidly almost reaches the peak of the value rectifier voltage with the first few cycle of the capacitor attempts to charge with the peak. The value rectifier voltage anytime the diode conducting tends to retain the charge when the rectifier output falls zero, but the capacitor cannot discharge immediately. The capacitor slowly discharges the load resistance during the time of the rectifier non-conducting. The rate of the discharge of the capacitor is determined the value of the capacitance value with the load resistance capacitation load resistance value over the RC discharge time of the circuit is relatively long. A comparison of waveforms of shown figure 416 view A and view B illustrate the addition of the capacitor 1 the circuit result will increase the average of output voltage and the reduction in amplitude with the ripple component of the ER that is now normally present across the load resistance. Now that you will consider the component cycle for the operation with a halfway rectifier, the capacitive filter C1 load resistor, and shown figure view A with the 417 capacitor filter, assume with it large enough that ensure the smallest reactance of the pulse rectifier current with the resistance of the load resistor, but is assumed to be much greater with the reactance for the capacitor 1 input frequency. When the circuit is energized with the diode conducting the positive half cycle of the current flow through the circuit with the cuff of the capacitor 1, the charge of the capacitor 1 will charge approximately peak value with the input voltage. The charge less peak value with the big cuff of the voltage drop the cuff of the diode 1 view with the figure A with the charge C1 capacitor 1 heavy solid line with the waveform illustrating view B with the diode cannot conduct the negative half cycle through the anode diode 1 negative with respect to the cathode during the interval. Capacitor 1 discharge of the load resistor the discharge of the capacitor produced the downward slope over the indicating the solid line with the waveform view B with the contrast abrupt with the fall with the AC voltage peak value to 0 the voltage across the capacitor 1 through the load resistor during the discharge period with a gradually decrease until the time the next half cycle or rectifier operation. Keep it in mind with the good filtering filter capacitor showing the charge for the fast up of the discharge and little as possible. 417 show the capacitor filter circuit with the positive negative half cycle with the positive half cycle of the transformer diode 1 capacitor grounded resisting load capacitor charge and sim waves negative half cycle of the transformer 1 D diode capacitor 1 resistor load capacitor discharge amount of discharge. Some practical value with the capacitor 1 and the load resistor ensure the more left with the gradual decrease with the discharge volt with the substantial charge of the lean for the capacitor at the time of the next half cycle of the operation. As a result, no current flow over the diode until the rising arc of the input voltage over the anode and diode exceed the voltage of the charging of the remaining capacitor 1 charge with the capacitor 1 cathode potential for the diode. When the potential anode exceed the potential for the cathode, the charge of the capacitor 1 the diode again conduct with the capacitor 1 begin with the approximate peak value of the applied voltage. After the capacitor has charged with the peak value of the diode will cut off, the capacitor will start with the discharge with the sense of the voltage, fall with the input voltage of the diode, and considerable more rapidly with the decrease of the capacitor conducting to the cathode quickly becomes more positive the anode, the decrease of the site ceases to conduct. Operation simple capacitor filter using the whole rectifier, basically some of the discussed the whole halfway rectifier. Referring to figure 418, you should know that the discovery of one of the diodes always conducting either alteration filter capacitor charge with the discharge during each of the half cycle. Know that each of the conductors conduct only a portion of the time of the peak secondary voltage is greater than the charge across the capacitor. Figure 418 shows the full wave rectifier capacitor filter, transformer T1 winding capacitor diode 1 and 2, and the on series with parallel circuit with capacitor and load resistor. Another thing to keep in mind with the ripple component of the output voltage of the AC voltage of the average of the output of the voltage of the DC component output and the filter capacitor offer the relatively low impedance of the AC with the majority of the AC component flow with the filter capacitor the components are therefore bypass shunted across around the load resistance and the entire DC component, or the voltage average flows through the load resistance. Statement can be clarified with the formula of the capacitive reactance. In a half-wave full wave rectifier, first you must establish some of the values as of the circuit. Half-wave rectifier frequency rectifier output 60 Hz value with the filter capacity 30 microfarads or in load resistance 10 kiloohms. You get 1 on time with capacitive reactance equal to 1 times 2 times the frequency and times the capacitation, frequency capacitation, farads times the capacity, 159 times 60 times 0.33, 88.3 ohms. Frequency rectifier output 124 hertz value with a filter capacitor of 30 microfarads, load resistance 10 kilo ohms. 1 or 1.59 times the FA frequency microfarads, or the frequency time of the capacitation, 159, 416, 44 and 16. You can see by the calculation doubling the frequency of the rectifier, you can reduce the impedance of the capacitor by 1/2 the level of the AC component of the path through the capacitor more easily. As a result, the full wave rectifier output is either filter than the half wave rectifier. Remember, the smaller capacitive reactance of a filter capacitor will result respect the load resistance then better than filter action, since capacitive reactance equal to 2 times the pi times the frequency times the capacitation. Large possible capacitors provide best filtering. Remember that all the load resistance is important consideration. Load resistance is made small load resistance and load current increase, the average output voltage of the average voltage decreases. The RC discharge time is constant direct current of the value of the load resistance. Therefore, the rate of the capacitor voltage discharge direction current, a function of the current through the load. The greater load current, the more rapid discharge of the capacitor, the lower average voltage of the output voltage. For the reason, same capacitive filter seldom with the rectifier circuit that must supply with a relatively large load current. Usually, simple capacitive filter conjunction full wave bridge rectifier provides improved filtering because of the increased ripple frequency decreases capacitive reactance filter capacitor. Alright, your LC choke input, and we're going to cut the tape there.